Oh, sorry. Oh, hello, everybody. Good afternoon, and welcome for the keynote speaker, uh, Julian Togelius, on machine learning revolution in procedural content generation. Julian Togelius is an associate professor at the Department of Computer Science and Engineering at New York University. He has previously worked on IDS AI in Lugano, Switzerland, and the IT University in Copenhagen. He works on artificial intelligence for games and on games for artificial intelligence. His current main research direction involve procedural content generation games, general video game playing, player modeling, and fair and relevant benchmarking for AI through game-based competition. He is the editor-in-chief of the IEEE transaction on game, and that's it. And we are very pleased to have you here virtually in Brazil.
Thank you. Thank you so much, Eber. I'm very happy to be there.
Okay.
Sorry I can't be there in person, but...
Next time, Phil, perhaps. So go ahead.
All right. You see my screen? Okay. Hey, everybody. I'm Julian Togelius, and thank you very much for the introduction, Jebber. And I'm here to talk to you about the machine learning revolution in procedural content generation. So I represent New York University, my main employer, and Model AI, which is a game AI startup that I co-founded. So I think it's customary to say a few words about who I am to introduce myself to you. So I'm originally not from US or Sweden, or US or Brazil or something. I'm from a town called Malmö in the south of Sweden. I grew up there. I finished high school quite miraculously, as I was so bad at mathematics and almost failed out of it. So I decided that I didn't want anything to do with engineering. I studied philosophy and psychology to understand the mind. But gradually, I sort of edged closer to computer science so I can do artificial intelligence research, because I realized that to understand the mind, I needed to build minds. So when I started my PhD in Essex in the UK, I realized that I needed to, or my plan was to use evolutionary computation to evolve neural networks to control robots. But robots, I discovered quickly, were really, really slow. And they had lots of problems. Batteries went flat, tires went flat, they needed to be repaired, and so on. So I discovered that I could do the same research much faster using video games. And while I was at it, I also discovered that you can use games to improve artificial intelligence in many ways, but you can also use artificial intelligence to improve games. So I got engaged in finding new uses for AI to improve games, such as modeling players, player experience, and replicating player styles, and generating game content. So I'm still motivated by what I want, understanding the mind and so on, but I'm also motivated by making games better. I worked in a couple of different places in different countries, and now I'm here in New York, which is usually a great place to be. One of the big things I work on is procedural content generation in games. So procedural content generation is where you generate some of the game content automatically, either as the game is being developed or as the game is being played. And procedural content generation has been around for a very long time in some kinds of games, even since the early 80s. Back in 1980, when Toy and Wakeman at the University of California, Santa Cruz wanted to they wanted to play Dungeons and Dragons on their computer, but they didn't have enough space on their hard drive to sort of encode the Dungeons and Dragons adventure, and they wanted to play something that they hadn't done before, so they created Rogue, which includes its own generator of dungeons. So every time you play it, you have new dungeons. Also behind here, you can see in the screenshot, ironically called Front, you have Elite, which is a a game from the early mid-80s, which is a space flight sort of simulator where you fly around and you have thousands of planets available, and each planet has space stations, spaceships, and all kinds of things. But all this fits in memory on a tiny computer of the time, like 64 kilobytes of memory, which is because every time you come to a new star system, the whole star system is generated for you. And if you think that we've gotten past these memory problems, now here at the bottom left of the screen, you can see a screenshot from No Man's Sky, which is a game which is extremely impressive. It's still in development, and you are traveling a galaxy which is literally too big for any human to ever explore in a lifetime. There are millions and millions of planets, or billions maybe, I don't know. And there are many other games that use some kind of, the key to this game working at all is that everything is generated. We also have Spelunky, you see here behind me, which is like a very popular sort of indie platformer. We had the games in the Civilization series, where the core idea is that every time you play them, you have a new world to explore. There's so many games where procedural content generation is used in some way. It is becoming, even in very mainstream titles, procedural content generation is usually used to create subquests, to create vegetation, to create like small features of the terrain and so on. Modern game development would be very hard without procedural content generation. So I've been working for a long time on seeing if we can extend this. Can we take this further? Can we create new types of games that build on procedural content generation? Can we generate games from scratch? Now, one thing, if you follow what happens in artificial intelligence at all, you may have seen that these days machine learning is everywhere. In the last 5 years or so, we've had this revolution where things that were previously done with painstakingly hard-coded algorithms, you sort of write some list of rules or something, or were done with very special purpose algorithms for image recognition or misconstruction. This is now all done by deep neural networks. You train a neural network on lots of data, and then you have it to generate things or recognize things or play a game or control a robot or something like this. And it's quite breathtaking what machine learning has been able to do in the last few years. Curiously, though, there is very little deep learning going on in games. And in particular, there's very little deep learning and machine learning in general going on in procedural content generation. So why is this? And let's go back to the basics to sort of explore this question. So how could you create a game content generator? So something that generates levels or quests or maps or game rules or something like this. There are many ways of doing this. One idea is to send a set of rules by hand. You have these constructive approaches where you have a lot of ad hoc pattern-based methods, which is very common. If you look at Spelunky, for example, it has a number of room patterns, and then it uses random variations of those. You have fractal noise, Perley noise, for example, is common there, cellular automata, and so on. Another family of methods is to design objectives or constraints and a representation by hand, and then use some kind of search. So you can search with an evolutionary computation, or you can search with constraint solving, or you can search with particle swarm optimization, or something like this. So these have been quite explored a lot in literature in the last decade or so. Some may be absolutely tired of methods for using evolutionary computation for designing levels, for example. I may have myself written about 50 papers about it or something. Now, yet another possibility is that you learn how to generate the content somehow. You use machine learning. So the basic idea of what we call PCGML, we put out a survey paper on this 2 years ago. Procedural content generation via machine learning is that you train machine learning models on some corpus of existing content. For example, existing levels for a game or existing characters could be something else at a game or something, and generate new contents. And there's a number of useful methods. There's n-grams, Markov chains, there's deep learning, and so on. Let's look a little bit about what I've been done. Let's start with something extremely simple. N-grams is sort of the original sort of sequence learning methods. N-grams date all the way back to Shannon's work in the 40s. The basic idea is that you simply build up a table for, we have strings, you learn on strings, you build up a table. After each character, you can, you list the probability of a next character occurring. And n is a number of previous characters and a new character depends on. So at 3 gram, for example, would look at which characters are most common after the 3 previous, after a certain combination of 3 previous characters. The larger n, the more training data you need to sort of create meaningful probability distributions. This is very commonly used for predictive text. This is like what's used for predictive text in old mobile phones, the feature phones from like 20 years ago. Your old Nokia phone uses n-grams to predict the next letter or the next word. More modern phones use recurrent neural networks and so on. The insight here is that it's a very simple method. You can use it for strings, but you can represent lots of game content as strings. To take Super Mario Bros. Levels, we did a very, very simple experiment where we trained n-grams on the 20 levels from the original Super Mario Bros. Game, the one from 1985. And depending on your n, you get different kind of levels. So if you have n is equals to 1, you get, as you see at the top here, levels that are very broken in various ways. You get half pipes. And I'm not talking about half pipes as in skateboards. You get pipes that are like somewhat broken, and you have a couple of other sort of strange sort of situations. I'm not sure this level is fully playable. I think it may be that you can get, but there might be some jumps that are impossible. Now, if you use n equals 2 instead, it gets better because then you can reproduce complete sort of more lifelike structures. And as you can see, this looks much more like an actual Super Mario Bros. Level. And if you look at n equals 3, then you start getting more structures. And these, you saw in n equals 2, you have this staircase which goes down and up again. In n equals 3, you don't get that. N equals 3, in fact, you start reproducing little chunks of existing levels. The problem is that you don't get much further than that because you don't have more training data. Another idea you can do is that you can do a new revolution. So evolutionary computation to train neural networks to produce to sort of learn to produce something. So this can be used in very many different ways. One analogy here is that Amy Hoover produced a system where it predicted different levels of or different instruments in a song from the other instruments. So, for example, from the drums and the bass line, it could predict the guitar solo, or from the guitar solo and the saxophones, it could predict the bass line, or something like this. And we thought, why not look at a level in a video game like a set of different instruments? So one instrument is where the enemies are. Another instrument is where the platforms are. Yet another instrument is where we have gaps in the ground, for example. And then you can input a sequence of previous previous values for each instrument and output the new instrument. So this is creating bricks on existing inputs. And this worked not so well. It turns out that almost certainly the lack of training data was hampering this effort significantly. Now, continuing on this idea of like looking at different parts of content in or different aspects of game content as separate voices, separate instruments, You can look at this in strategy game levels, for example, and you can see you have a level, and based on where you have, for example, bases and where you have enemy spawn points, maybe you can predict where there are resources. The idea here is that this could be very, very useful in an interactive design tool where you actually design some parts of a strategy game level, and the tool suggests where to put the other parts. So say that you draw some mountains, and it says, well, here is a good spawn point, for example. And we did this for StarCraft, and using deep convolutional neural networks with relative success. There was some issue with overfitting and the issue of finding. What you see here, we tried a number of different aspects here. What we see here is you feed in the height map, and it predicts where there would be resources. It gives you nice sort of levers, so you can basically say that if you want more resources, where would they end up? If you want fewer resources, where would they be? The problem is that there seems to be some amounts of overfitting in this. Another sort of very powerful, the last decade or so of deep learning has come up with so many really powerful methods. Another really powerful method, which is a sequence learning method, is long short-term memory, which is a recurrent neural network, which is very often used for sequence recognition and prediction. So if you look at the phones you have these days, like modern mobile phones, this is the kind of machine learning model that's used for text prediction. That's why it can eerily suggest whole lines of emails you're about to write. So in particular, Gmail's automatic reply feature uses long short-term memory. And could you use this to create game levels? Yes, you can. So here is Aaron Somerville's work. I should have a reference. Aaron Somerville, back when he was at University of California, Santa Cruz, and Mike and Matthias, they did this work where they predicted Super Mario Bros. Levels. So they inputted not only levels, but also the path that agents have taken through the levels. And the paths are very important because it teaches the machine learning model how to make paths that are unbroken. So in other words, how to make player levels that are playable. And this is an example output with a example player path, which is clearly something you can follow. So clearly Mario can play this level. Another really fun thing that Aaron Somerville and Mike and Matthias did, Adam Somerville, sorry, was using LSTMs to generate magic cards. So Magic the Gathering is a collectible card game which has a large amount of cards. And when I say large amount, at least thousands, maybe tens of thousands. I'm not really sure. There's a lot of it. Each one of them has different stats. It has a cost, it has attack, defense, and it has classes that the different cards belong to. And it is and they have descriptive text, which is in English, which describes what the card does, the very special effects it has. So here, this long short-term memory module was sort of asked to produce a new card, which would be a legendary fungus shaman, which is, I'm trying to imagine what a fungus shaman would be like. So it creates a card with cost 4, attack 4, defense 3. It's a legendary creature, a fungus shaman. And it says that whenever a creature enters the battlefield under your control, you may put a 2/2 green wolf creature token with haste onto the battlefield. And your first reflection seeing this is like, wow, this looks like a completely acceptable Magic the Gathering card. I mean, it has reasonable values. The text is complete and proper English, very understandable. So maybe we should play this. But if you know something about the game, then you realize that this card is horribly broken and will immediately destroy your game. Why? Because what it says is that whenever a creature enters the battlefield under your control, you may put a 2/2 green wolf creature token with haste onto the battlefield. This means that whenever you put a creature comes under control, you can put another creature there. So you can put another creature. So you can put another creature. So you can, in the instance you get this card, you can get an infinite amount of green wolves, which is handy. Even worse, all these green wolves have haste, so you can create 1 million of them and attack with them immediately and win the game no matter what. So this is an example of a problem that basically all machine learning models we know of have at the moment, which is that they don't model the properties of game content that make it playable, that make it not break the game. They very often do some kind of surface level aesthetic modeling, and it models some parts of Magic the Gathering cards very well here. It creates very nice sort of English text, for example, but it doesn't take into account, and you can't reason about that this card is in fact game breaking. Now, let's look at another very popular method in modern machine learning is generative adversarial networks. This is something that was only invented back in 2014. The idea of a generative adversarial network is that you have two networks and you train them intermittently. You have a generator and a discriminator. The discriminator is trying to distinguish real artifacts from fake generated ones. And the generator is trying to generate artifacts that fool the discriminator. So you have kind of an arms race. This is essentially the same idea as competitive coevolution, which has been used in the evolutionary computation community for a long time. But here it works with gradients instead. Explicit gradients and gradient descent. What we see here is that this has been extremely popular for generating, for example, images of faces, bedrooms, and all kinds of things. Can we use that for game content? Yes, we can. Here's an overview of what it is. We have a training set, and we have a generator. Generator generates fake images. Discriminator is trying to tell the real ones in the training set from the fake ones, and it improves to do that, whereas the generator is trying to fool the discriminator. The problem with this is that all these various methods, they're good at producing faces and cars and bedrooms and so on, but it's always slightly off. So for example, you create parts with one wheel is bigger than the other, or like a face that looks great, but there's something really strange about the background and off perspective and so on. Same thing with language models, so LSTMs and transformers. You've seen GPT-3, for example. They produce this surface level text, which sounds great, but it's not coherent. There's no meaning to it. And the problem with game content is that this may not be enough for game content. So if you look at a game level, and this argument applies to many types of game content, like quests and characters and stuff, it is like an image, because it has these sort of visual aesthetic qualities. It needs to be nice to look at. It needs to have a, color and geometry balance, to be sort of readable. You can look at it with your eye and like, yeah, this makes sense. But it is also like program code. You need to compile and run it in a sense. So basically, if a game level, it can look as nice as you want, but if you can't win it, if you can't sort of complete the level, it's worthless. It's worse than worthless, basically. It's like malicious, misleading. In a sense, it sort of crashes the game. And also the same thing, if it's possible to win it without doing any of the things you're supposed to do, that's also really bad. So in a sense, it's more like program code than levels. It has very different sort of constraints, but it's also like an ecology. So things need to be very precisely tuned for this game level to be interesting and to care. So basically, and multiplayer maps is another example in FPS games. All this is very much true. And this is not what our current machine learning methods are really set up to model. They don't know how to model this. So one idea for how to overcome this is to combine learned models with search. So you train a model of levels or other content using some supervised or self-supervised learning, for example, again, on an LSTM or convolutional net or whatever. And this model takes some kind of input and vector of real number, and then you search the input space for good content. So the objective function uses this model that you train to transform from input to output. In evolutionary computation terms, it is a genotype to phenotype mapping. Or in search-based procedural content generation terms, it's a representation. The idea is that you first learn a model and then you search. So here's a great example of this. It's a paper that came out 2 years ago. It actually builds on a previous paper of mine, but was done by this set of authors, led by Vanessa Volz, who's currently working for us at Model AI. It's about evolving Mario levels in the latent space of a GAN. So you train a GAN on a Mario level, so it can produce level segments. You search the latent space of the GAN for level segments with particular properties. And the idea here is that to sort of visualize it, you have the real levels as inputs, and these you take samples of those, and you have a generator producing generated levels, and these are fed into the discriminator, which is trained to discriminate among between them. And then you have the generator. Oh, well, this is the GAN training process, phase one. So after you've done this is a regular GAN. You just basically intermittently train the generator and discriminator, generator, discriminator, generator, discriminator. And you train this until you're done. And it generates lots of Super Mario Bros. Scenes that look pretty decent, but you have no guarantees. And in the next, you see here that when you train the generator, it just takes noise as an input. But in the next phase, we keep the generator and just freeze it. We don't do anything with it. We input, instead of noise, we input a latent vector. So you can search the space where there used to be noise. And this is trained using an evolutionary algorithm, in this case, a covariance matrix adaptation evolution strategy, in order to find levels with good properties. So first you learn, then you search. This is an overview of this, of the architecture, and what happens if you do randomly sample levels. They look okay. If you mutate it a little bit in input space, it mutates the output a little bit, which is good. And then you can optimize them. You can, for example, maximize the number of jumps. You can minimize jumps, create unplayable levels, create ones with broken tiles, etc. It is you can basically search for, together with an agent that tests the level, you can search for particular features. And here's, for example, one level that is it's produced to have increasing difficulty. It's very easy in the beginning, and it gets worse and worse. And then in the end, well, you have lots of enemies and stuff. So going back to what PCGML in general. So this nice combining search with learning is a very important direction to look at. Now, if you look at the main problems, we have output, which is pretty, but it's not correct in many cases. It's not provably playable. It's not balanced, for example. But as we just saw, you can combine machine learning with search, and that helps a lot. So SBPCG stands for search-based PCG. Another big problem is the amount of training data, and yet another one is the diversity of output. What do we mean by the training data problem? Well, if you're going to create procedural levels or characters or something from a game, then you need to actually have something to train on. Now, a typical game doesn't have that much content, and if it has a lot of content, you may not need a PCG. It's sort of a chicken and egg problem. And if you, for example, are creating a new game and you only create 5 levels by hand, this is often too little for real sort of, machine learning to learn something from. And there's often, like, even if you have the content, like extracting it's hard. So one grand challenge that people have started addressing, but not very much, is to learn reusable representations from the content in multiple games and fine-tune a new game. One thing that we'd love to be able to do is learn from, like, say, 100 different platform games, and then try to sort of produce levels for a new game by just telling it what's the difference between this new game and the one we trained on. We don't have that yet. Some people, Anurag Sarkar and Seth Cooper at Northeastern in Boston, and Sam Snodgrass, who works at Model AI with us in Copenhagen, have been making some progress towards this. One method that we advanced recently to sort of overcome the training data problem is bootstrapping. So the idea here is that if we can test if a level is good enough using some constraints, then we can train on just a little bit of content, and then if it produces new levels that we test and we say that they're good enough, we just add them back to the training set. So we gradually expand the sort of what the training set covers from very little to more and more. So here is our architecture. This is like somewhat complicated for what we call a self-attention generative adversarial network. And what it does, this is a paper published this year in IEEE Conference on Games. Every time you produce new levels, it adds them back in training set and retrains this attention-based generative adversarial network. Now, here's another problem. If you train a model on some data points, and then you sample this model. So most of the samples from the model are supposed to be, you can assume that they're going to be inside the hull formed by these points. So it's somewhere in between. It's some interpolation of what you've already seen. You can talk about that new content is like recombinations of old content. So another grand challenge for PCGML is to, if you've been doing machine learning on old content, how do you produce stuff that is radically unlike what you trained on, but still good? So one approach we advanced a few years ago for this, we call it Delanox, is where we interleave exploration and transformation. So we have novelty search, which is quality diversity, and a type of quality diversity algorithm that basically is a divergent search. It doesn't sort of optimize for a particular thing, but it goes, it tries to find new solutions with an autoencoder. So first we train on existing content, then we search in the space of this content for things that are very different from what we trained on, and then we retrain the autoencoder on the new content, etc. This is, I think, a promising direction to go as well. And then we have the general idea of quality diversity, where you have a lot of different sort of algorithms such as map elites and novel search with local competition, where you're trying to not only optimize for a given objective, but you want to explore, you want to produce output that's as dissimilar as possible. Recently, we've seen some combinations of PCG-ML with quality diversity, and it's very promising. This is a chart from our PCG-ML survey paper from 2 years ago, where we're looking at what's the possibility space, what has been done, what has not been tried. And there's a lot of interesting new things that we have not tried. And this is even before we started looking at combining search with machine learning. So procedural content generation through machine learning is like a booming sort of subfield where there's a lot of work to do currently. And there is a number of like resources for training data available. There's a lot more that can be done. And this is the point where I tell everybody that please don't hack Super Mario Maker and take all the levels that Nintendo has and make them publicly available to train on. I would totally not want that, because that would be illegal. So please don't do that. Anyway, would be kind of nifty, right? Right. So we talked a lot about training data. In the minutes I have left until I get booed off stage, no, until I should be done. Let's ask the question, what do we do if we don't have any training data? Can we use machine learning even in the absence of training data? So in a new paper that was published this year at 8, Procedural Content Generation through Machine Learning, we cast the whole generation problem as an iterative task. So whereas evolutionary computation in search-based PCG, you see it as an optimization task. Here we see it as an iterative task. So instead of generating whole content, we see that there's a Markov decision process, and the task becomes taking the next action that improves the content. So the idea here is that you have an agent, but the agent is not something that plays the game. An agent is something that builds or changes the content, such as a level. And the representation is the current state of the level, and it gets rewards based on how much it improves the level in the end. And it uses standard reinforcement learning algorithms. I think we used actor critic, so A2C in this case. There are many different ways we can actually represent the problem here. You can look at it in a binary way where you on like different problems here. So the binary here is a problem where it's about digging creating a map which has the longest, shortest. No, it has the map with the longest possible path in it. We have Zelda, which is a version, it's a very simplification of the overworld of Legend of Zelda. You move around, you slay monsters, take the key, get to the door. You have Sokoban, which is a classic sort of box pushing puzzle. And there are different ways of transforming this to generation process, or casting it as a Markov decision process. In a narrow representation, you are basically moving around in scan lines across the level. You see here that this is like a CRT. It moves across the level, and at every point it decides, should it build something else, or should it change this tile, and into what, or should it not change this tile? So it gets a very local representation. And it is rewarded for, in the end, producing, in this case, the longest possible path. We have the turtle representation, where we're actually seeing, this is more like an actual game agent. It's moving around, it sees its local environment, and it is can choose to sort of build or not. So it is rebuilding as we speak here, and trying to create a level. And we have the wide representation, where it can edit anywhere in the level, and add or remove tiles and change them into something else. To make this possible, one really crucial detail here, you can read more in the paper. In the paper, it just starts with PCG-RL, but was that we have to limit how much it can change of the level in each episode. Otherwise, it learns not a content generator, but it learns one single content artifact. So not a level generator, but just one level. And this is, we're trying to understand this better and do more research on it. And the results are that it can pretty well create good and playable levels, at least as long as they're small. We see here the results for like all the different combinations of representation and problem. We're working on this to sort of bring this into like an interactive tool in various ways. Right, I see I'm out of time here. I will finish with this slide as I usually do. I have a popular science book about some of these topics, which is easy and nice to read. contains no math. I wrote it so that my parents would understand it. I think my mom has actually read it, and she says she likes it. I'm not sure I can trust her, but anyway. And we have a more heavy-duty textbook, Artificial Intelligence and Games, by Jorgos Yanakakis and myself. We are going to try to run a summer school in AI for games next year in Copenhagen, pandemic willing. And the journal I am the current editor-in-chief of, IEEE Transactions and Games, is happy to receive submissions on this kind of work. And with that, I think I'm done. And I'm happy to take any questions now if Jebber thinks we have time for it. I will also join the Discord a little bit later on, perhaps not now, but perhaps in 1 or 2 hours. And then I will make myself available on Discord for just general chatting. So thank you, everyone.
Thank you, Julian. Thank you very much. So we can ask questions. We have another first question. I will read it. To avoid, it's from, yes, can you read it?
Yes, to avoid generating unplayable levels. We
that's
the player as an additional discriminator. Train an RL agent to play the level and say if this level is an original or generated one. Yes. So in the Marugan work, where there was the Vanessa Volz paper, where again is first trained and then is searched. So the fitness function actually uses a simple player to test that level. We've done this several other times as well. The problem with this is that it's slow. It's slower than just using some other features, but it is a very good idea. It's not an RL agent in that case. It's actually okay, so here's the real problem. Training an RL agent to do this, it's extremely slow. We've tried this. We have something we call generative playing networks, which trains a level generating agent and a playing agent at the same time. And it's very hard to make this work because it is so slow. But, what is one of the reasons, but using a tree search-based agent to play the level, if you have one, is a great idea. So that's why they did in the Vanessa Volz paper.
You have 2 more questions?
Of course.
Okay. Can you read it? What about using tools like this to optimize not only levels, but things like running speed, jumping high, things that like those variables that are hard to adjust?
Yeah, definitely. So game balancing is definitely an interesting topic. And I've not seen any use of machine learning for it. I've seen uses of evolution for it. So Vanessa Volz, who was again working with us at Model AI and was leader of that paper, has been doing some work on evolving sort of parameters of games to make them more balanced. And we've done in the past. So Fernando Silva, who was a PhD student co-advised by me, also Brazilian. He's currently working at Electronic Arts in California after finishing the PhD with me. He led a series of papers where we used evolutionary computation to balance the board game Ticket to Ride and found out lots of interesting things about it, including we found a bug in the game, which is pretty cool. After a game that sold millions of copies around the world, and evolutionary computation found a bug, a sense in a state which is unplayable in the game. But yeah, so I think evolution is the main tool there. Maybe you can use reinforcement learning as well.
Okay. The first question was from Paulo Serafim, and this last one was from Gabriel Ritter. We have a next one from Daniel Perazzo. Is there any research on how to automatically, quantitatively evaluate generated levels?
Yeah, there is a lot of research on it, actually. And it comes in different guises. There is work that uses a player model and basically tries to sort of first train based on a number of levels that based on observation number of real human players playing a level and creates an approximator. But it's also that we uses artificial agents. I can't think of exactly what to send you to right now, but it's more like the ideas behind it. I can possibly give you more links in the Discord later on. There is the idea that one way of automatically evaluate it is in terms of skill differentiation. So what's a good thing with a level? It's one that which can be beaten by a good agent, but which cannot be beaten by a hard agent, by a bad agent, and which a medium skill agent would do medium performance on. And we call this we call it skill differentiation essentially. So I have some papers I can post later on that tries to do this on various levels and games.
Thank you. Have still some questions.
Of course.
Igor Rebouças ask, what about your thoughts on PCG plus human level designers as a development process? My
general thought on this is that that's the future. I think that is definitely where we need to go. The big sort of, basically because completely automated game design is not going to take the jobs away from human designers anytime soon. But these kind of AI tools and PCG tools provide amazing abilities to sort of, if used right, they can really amplify what we can do as human designers. So we've done a couple of different experiments in this. We have been using one of the more fully realized, where we build a complete sort of PCG-based interactive mixed initiative design assistant for Cut the Rope, the mobile puzzle game, which is called Ropossum. The problem with this is many of these tools are built for a particular game. So Tiago Machado, who was a Jabber student once, and then my PhD student, his PhD was on building a system that would try to do this in a generic way. So using our general video game AI framework, this system called Cicero would give advice and suggestions to humans at the build levels and automatically evaluate them and so on. It's a very interesting sort of proof of concept. The problem is to actually make this work in a development environment that humans actually want to work with. So that's a problem. But I think it's the future. We should work towards it.
We have another question, perhaps the last one. No, Luis Chamovics, how to deal with the problem of PCG versus game balancing, especially in scenarios such as CCG, where, as you mentioned, an unbalanced card can break the game.
Yeah, it's complicated, right? We had a paper back in 2012, I think, where we tried to do balance a game called I'm blanking. My mind just went blank. It's not really a collectible card game, but a card game with a lot of different cards. Dominion is the name. And by basically trying to find different card combinations, evolving card combinations will be very strong or very weak and so on, and try to find the outlier cases. I think that this is generally the direction you need to go, to basically try to adversarially test it. The evolutionary algorithms are great at breaking things. They find like configurations that break the game. But if you look at something like Magic the Gathering, where you have so many thousands of cards, it's just extremely hard. There's a little bit of work that's been done in Hearthstone, but even Hearthstone, which has hundreds of cards, it is very hard because there's so many possibility spaces. It seems that, from what I know some people who work in data science on Hearthstone and design, and inside Blizzard, and what they're doing is that they're just constantly keeping up with what players, weird strategies that players are are sort of inventing, and then try to nerf cards or buff cards to make things better. But yeah, I don't know. This is a good research topic.
Great. We have a question from Bruno Feijó.
Hmm?
Please, could you say more about imitation learning in games?
Yeah. Imitation learning is interesting because, I mean, imitating a particular, so basically sort of training an agent to play one level and having it play the same thing again, then that's that's simple. And but what you get is some kind of overfitting. It's not going to do well on other levels or other games or something like this. So the interesting question about imitation learning in game, so if you could solve this, this would be extremely useful, is how do you train on how a human plays one or several levels in one game, and then this transfers to other games? That would be very interesting. However, this is hard. So one approach we've been doing is called procedural personas. The procedural personas approach is that you're not using supervised learning to imitate. You're instead you have like some kind of tree search based player already, like using Monte Carlo tree search. And then what you're doing is that you're finding tree expansion mechanisms and reward functions, or like utility functions that make the tree search behave in accordance with the play traces you have collected. I can post those links in the Discord later on. So the procedural personas approach, I think, is much more promising for generalizing imitation learning, because you were not going to overfit to the same extent. Now, if you could have general imitation learning, that would be great for being able to automatically evaluate levels.
Okay. As you mentioned music, I will ask you a question as a musician.
Yes.
So most of the techniques you presented, in fact, work with the small windows, time windows.
Yeah.
This is very good to create a step-by-step fine-grained content, but this kind of technique misses the structural, let's say, the big picture.
Mm-hmm.
When generating music, for example, we have some structural constraints as chorus, for instance, that help us to guide this local machine learning. Do you think that we could try to figure out something in the game in the same sense?
I think a very interesting idea is to sort of train models at different levels of fidelity. So you basically have a machine learning model for the details, another one for the sort of meso scale, and another one for like the whole level scale. So this has been very, I don't know if you know NVIDIA's work on hierarchical GANs for phase generations from 2 years ago or something. And it seems to be a very powerful idea. They basically train GANs on different levels that take the higher level as input and then creates, sort of specializes it, gives it more details. I haven't seen this done in games. The problem again is the amount of training data, and this is something that needs to be handled at many different levels. Something that was published this year by a German research team called TOAD-GAN, so TOAD GAN. It was published at AID, this conference, just a few weeks ago, is one very cool idea here, where you basically have it basically learns at different levels of fidelity, but it uses sort of a hard-coded way of basically sort of increasing or decreasing the resolution. So it's a little bit hacky, but it gets really good results, and it trains on just like one level or something like this. I think there's a lot to learn also from looking at things like wave function collapse, which is a constraint solving case-based constraint solving mechanism that can generate complete patterns from very small examples. So I don't think it's impossible. I think it's possible, but we haven't really figured out how yet.
Okay, last question by Gabriel Rita.
Mm-hmm.
Could, and if so, how AI quantify the fun factor in games, in game level and mechanics?
This is this hard and contentious question. It's the first time I had someone going up on a public stage and actually making fun of me, like specifically in a keynote speech referring to something I'd done and basically saying that it was bullshit. It's exactly about this. It was Julian Smith. She's a friend of mine, but she was basically ridiculing my approaches at trying to formalize fun. So what we did was that I did a paper in 2008 where I looked at a set of theories. There's one by Ralph Koster, the game designer, which says that fun is due to learning. A fun game is fun largely because you're learning to play the game as you're playing it. This is so I tried to basically create the game generating system. This idea fits in very well with a number of ideas in machine learning, so Schmidhuber's principle of curiosity, and ideas in developmental psychology like Piaget and others. And I tried to create a game generation system that generated games which should be learnable. So the fitness function was whether another algorithm could learn to play it and how well, starting from nothing. So it shouldn't be super easy to learn. It didn't work very well, maybe because it was extremely computationally expensive. But I think this is in principle a good way to go. I think it's a very good way to go to find ways of find proxies of learnability and challenge factor. Now, this is only one aspect of fun. There's a bunch of other aspects of fun that I'll leave for another time. But this is the one I like most.
Okay. So thank you, everybody, for coming. And especially thank you, Julian, for accepting our invitation. It was a pleasure to us to have you here.
Yeah, thank you for inviting me.
Next time, perhaps in person.
Yeah, sounds great. I want to Caipirinha.
Go ahead.
No, that's great. Thank you so much. I will be available in Discord. Right now, I have to zoom out to a faculty meeting, but after that, I will pop into the Discord in the Keynote channel and answer questions in text, and I'll try to be available in voice at some point later on. So basically, if you hang around there in an hour or two, or feel free to just post things now, and I'll look at it.
Thank you a lot.
Thank you. Thank you so much. Have a great day, everyone.
Okay. You too.